Here we're looking at mechanisms, pharmacological mechanisms for treating worms. And first thing to say about treating worms is we've really got two different types of problem here. So there's two ways in which a worm can infect us. They can either get into our intestines, and we're familiar with that with small children and roundworms, or they can actually get into our tissues and cause considerably more damage. And of course the problem here is that they are hidden from the immune system. So let's focus then on worms affecting the intestines. And our main concern here is with two types of worms. The main ones are the roundworms and the tapeworms. The main tapeworms infestation with tapeworms, by the way, is quite often asymptomatic. You don't know you've got them until they start coming out, and then that can be quite noticeable. So main types of tapeworm that we see in the UK are species of Taenia. You're probably familiar with what the tapeworms look like. This is what they look like, and we become infected with them when we eat meat containing the larvae, especially if the meat is undercooked. And so they then enter into our intestines and have a great time. Question is, actually some species are transmitted through eating fish, which raises the uncomfortable question of whether you can get tapeworms from eating sushi, and unfortunately the answer is yes. Here is a salmon and here is a tapeworm growing in the sushi. Not in the sushi, in the salmon, sorry. As for roundworms, they are, as the name suggests, round, and they're the kind that parents of young children will be familiar with. So how can we treat these infections? There are really three ways of treating them. You can paralyze them by causing muscle contraction. You can physically damage the worm, and that can result in the immune system, that is your immune system, can then deal with the damaged worm. And then the third thing you can do, which is rather reminiscent of bacteria and protozoa, is you can interfere with their metabolism. And I'm going to give you some examples of each one. When it comes to interfering with metabolism, benzimidazoles operate by inhibiting beta-tubulin formation. So this thing, which looks like a giant sausage coming down from the top left, that's the tubulin, and it's being formed by polymerization of its constituent subunits. So normally what happens is these subunits build up the tubulin by being added to it step by step, but benzimidazoles interfere with that process and prevent the tubulin from forming. And here are some example molecules of that type. Another class of compounds, such as praziquantel, interfere with calcium signaling. There's praziquantel, and it interacts with voltage-gated calcium channels to increase the amount of calcium entering the cell, and that results in apoptosis. Another drug, piperazine, is another drug which acts on ion channels, and in this case it acts on GABA-gated chloride channels. So normally GABA binds to an agonist site, and that causes currents. But if you look at piperazine, it almost resembles GABA. You could put the nitrogen and the hydrogens together. You've sort of got this GABA-ish. And so what piperazine does is it mimics that GABA action, but keeps the channels open for a really long time. So far then, we've looked at drugs which interfere with metabolism, and for these we talked about the beta-tubulin drug, which is benzimidazole. We've also seen drugs such as praziquantel, which affects the calcium signaling. And we also did piperazine, which actually that's probably more to do, I think, with paralyzing, because what the piperazine will do is to opens GABA channels, and so that's going to cause paralysis, isn't it? So let's move that. Over here. So causing muscle contraction. And then we've got a bit of the immune system come across with me as well. Let's put that back. Oh, it's going. Oh well, you get the idea anyway. So let's just put the immune system back. Immune system. Okay. Piperazine. The other thing we can do to cause paralysis is to directly activate nicotinic acetylcholine receptors, and you can do that with drugs such as levamisole, and that does the same thing. It activates the nicotinic receptors, but then blocks them as well, and so it activates them, makes them open, then they desensitize, and so they get blocked, and so that also paralyzes the worm. And then another actually really important one is ivermectin. And this is quite interesting because what ivermectin does is it it potentiates glutamate. Now you've heard of glutamate receptors, glutamate gated, and this is the surprise, chloride channels. Why is that a surprise? We only actually get glutamate gated chloride channels in invertebrates, which is great because that means we can give it to, so basically we have glutamate gated cation channels which are excitatory, but invertebrates, and we don't have these, invertebrates have glutamate gated chloride channels, and ivermectin potentiate those as well. So that's why ivermectin is one of the reasons why it's so successful. You can just pour it on animals and it doesn't really affect people very much at all. So then, those are our methods of treatment for intestinal worms.